thing is, on the jobs, you have to ranking of all the jobs. Is that a list jobs? List all the jobs. I'm thinking it's so I just call this jobs.
Okay, let's move on. So, hope you're all moving along on your lab, that you got through the midterms okay. For those of you who have seen your midterm scores, we'll post a note on Piazza, but we did a very simple computation. We took all your lab scores up through Cash Lab, and those totaled to 24 possible points. We took your midterm, that was 20 points, and we added those together. So there's a number 44 is the maximum, and then we just normalized that to a range between 0 and 100, and just did the usual cutoff. So 90 plus is an A, 80 is a B, and so forth, and reported them. So midterm grades are not part of your transcript or your official record. They're just a tool to help you, and maybe your advisors might see them as well, to get a sort of heads up of how you're doing. So we don't get too stressed about how we assign these grades. We just give you a sort of general view. So today, we get to talk about something that we've been promising all term, which is virtual memory. You'll remember back when we were talking about machine code and we talk about all the ways you can compute addresses, but those addresses are always this mysterious thing, this 64-bit quantity with a lot of F's in it typically, if it's up on the stack. And we said, just wait, we'll talk more about how that really works later. Well, today is when we start talking about virtual memory, which is the sort of, the observation, you know that we've said at any given time, a computer can be running many processes, easily 50 or more processes if you include all the various daemons that are monitoring network traffic and supporting printers and doing various things in the background for you, as well as the programs you have that you're running, the application programs and so forth. And we've seen that each of these has an image that it has a totally independent range of addresses over some very large range of values. And somehow each of these processes thinks it has some range of addresses, and yet they're all sharing the actual memory of the computer and managing not to trip all over each other and mess each other up. And that's the idea behind virtual memory. It's giving you the illusion, the virtual, that somehow you've got access to a lot more memory than is actually on your computer, and somehow your memory is independent of the memory of the other processes that are running. So that's the virtual part of it. And so we'll talk about this both today. Today's more the sort of conceptual ideas, and then the next lecture is more concrete with how this is actually supported in Linux and some details of the processors and things. And the interesting thing about it is virtual memory is actually loaded with a whole bunch of issues, and it's a huge topic on its own, and it sort of goes across multiple levels of a system, because there's actually hardware support for virtual memory built into the processors and so the hardware design. But a big part of it is managed by the operating system. And so it's interesting, usually in a class, they're talking hardware, they're talking software, and when they try to talk virtual memory, they kind of have to omit half the story. In this class, we sort of talk about everything, although we don't go into a lot of detail, but we get to really talk about this sort of integration of the hardware and software to support virtual memory. But virtual memory is also one of these ideas that has had layered on top of it all kinds of different capabilities that it supports. So one is it's sort of a cache. You can think of it uses the memory. I'll just call it the DRAM because that's the technology you have. And a typical computer, my phone has 2 gigabytes of DRAM, and some of your CPU, your laptops have up to 16 or 32 gigabytes, and a big supercomputer might have hundreds of gigabytes or even a terabyte of DRAM. So you can think of it, though, even though that's a lot of memory, several gigabytes or more, it's not as much as your virtual address space. As you know, the addresses on these systems are 48 bits, and 2 to the 48th is about 256 terabytes. So it's a lot of memory that you can potentially reference conceptually. Of course, very few applications could really make that much use of it. But you can think of it that they basically, virtual memory is a way of creating a cache out of the DRAM that's caching the actual data of your program, which might be stored on a disk, for example. The other is it's a way, as we've seen, of creating a management scheme where we can have multiple independent processes, each of which has its own virtual address space. And the third is it provides protection. So for example, in your process that you're running are stored up in the address space above the stack, all kinds of kernel data structures that if you tried to access them, you'd get a protection violation, a segmentation fault or something like that. Because there's, for example, potentially cryptographic information up there and various things that you shouldn't be able to read, and certainly a lot of data structures you shouldn't be able to write. And so those are managed for you by the operating system kernel, so they're in your address space, but you can't access them. So we'll sort of pick apart virtual memory as serving all these multiple roles and how it supports them. So the basic idea is pretty simple, that in a sort of very, very primitive computer, and you can hardly even find these, uses what's known as physical addressing, meaning when there's an address generated by your program, it really is exactly an index into the physical memory, the actual DRAM that you're using. And this might be true of like a little microcontroller that's controlling your toaster or something, or microwave oven. But even nowadays, like a car has multiple computers on it, but most of them are actually full-fledged 64-bit computers. And my cell phone has, and your cell phones probably too, have pretty sophisticated processors. They all use virtual addressing. But just imagine a very simple processor that when it says this is the address, that's really the address. The idea of a virtual address is that there's a translation process. There's an indirect relation between what the virtual address is and what the physical address is. And as I mentioned, it serves a lot of roles. It's a very strong idea. So let's just use some terminology. We'll assume that in all cases our addresses are just a range of integer values, and that we're referencing bytes. That's not true on every machine, but it's good enough for today. And so we'll say that there's capital N different virtual addresses and capital M different physical addresses, where typically N is bigger and often much bigger than M. So I mentioned, for example, 2 to the 48th as a value of N, and 2 to the, 32 gigabytes would be 5 plus 35 bits of address. So 2 to the 35th, for example, for a 32-bit, 32 gigabyte memory. So the idea then is to, we'll keep track of those numbers and talk about that relation. So as I mentioned, the first part of it is this idea of using the DRAM as a cache, so that at any given time, you actually only have some subset of the actual range of memory that you might want to access resident within the processor. So the idea of it then is that there's, we logically divide our memory up into pages, and we'll say that the page is some number of bytes, typically a power of 2. So a typical number would be 4K bytes, 4,096 bytes, makes up 1 page's worth of memory. 4,096 being 2 to the 12th. And so at any time, then we'll say that there's some subset of the virtual address range of pages that are resident in the physical memory. And the other ones might not exist at all, or they might be stored on a disk. So we'll talk about then there being virtual pages, which is how your address space is divided up into these blocks of 4096 bytes each, or whatever the page size is. And then there's some range of physical pages, some subset of which are some subset of your virtual memory pages. And so this one shows that, imagine then that, as this picture shows, some of these pages might not exist at all. Some might be stored on physical memory, and then these gray ones, we're saying they're uncached, meaning they're actually sitting on your disk. So the sort of realities of the underlying technology have a huge impact on how we organize this system and how we implement it. So you've already learned a little about caches, the cache in the hardware system, which is a way of speeding up the access to the DRAM. When we normally talk about caches, we're talking about a way of making the actual memory references faster by having a subset of your blocks stored in a special hardware memory called the SRAM or static RAM that has faster access than the DRAM, the larger amount that when people talk about I have 32 gigabytes of memory, they mean how much DRAM they have. So the sort of range is like 1 or maybe at most 2 orders of magnitude speed up you get between DRAM and SRAM. And that, by contrast, the relative speed of accessing data off of a disk is many thousands of times slower than reading it from memory. So especially if you think about a disk, the sort of traditional mechanical disk, have these platters that are spinning, and they typically spin at around 7,200 RPMs, which sounds pretty fast. It would be if it were a car engine. But if you think about that, for any given position on that disk, for it to sort of make the rounds, let's see, 7,200 RPMs is like 120 rounds per second. So it takes close to a millisecond for that particular bit on the disk to actually get under the head where it could be read. Also, the head is on a movable arm it has to position. So the point is, whatever you think about the technology, the mechanical disk has access times on the order of, that are measured in milliseconds, whereas DRAM time numbers are measured in nanoseconds. So many orders of magnitude speed difference between them. The other property of disks is that it takes a while to get to the first bit of a read access, but then you can read a whole block as fast as that data sort of rotates underneath the particular head. So it's a case that the first bit takes several milliseconds to get, but then from there you can be reading at a pretty good clip as far as reading it in. So it means that all of this means that the design of a virtual memory system, even if we think of it as a sort of a cache, is way different from the hardware cache that we've looked at earlier. So in particular, we want pretty large blocks. So a typical number, as I mentioned, is like 4 kilobytes, as opposed to, say, 64 bytes in a hardware cache. And that's partly the property of this disk technology, that it takes a while to get that first byte, but then the successive bytes come pretty quickly, at a pretty good rate. So we want to sort of take advantage of that block reading capability. And the other is that we're willing to pay a pretty high cost for a fairly sophisticated mapping algorithm if it can reduce the miss penalty, our miss rate. So we know in caches, the actual structure is pretty simple. At most, you have a set associative cache where it does a mapping where there can be maybe 4 different places that any block could go. On a virtual memory system, we'll actually let it be fully associative, meaning any page can go anywhere. And we'll use software to implement the sort of mapping algorithms, because in the time we have to do a block transfer, like I said, if it's measured in milliseconds, the operating system can run 1 million or more clock cycles worth of computation. And it can spend some of that time figuring out, fairly carefully where would be the optimum place to place this page. It will also probably go and do some other process in the meantime. Question?
Does it, the replacement algorithm, does it consider what to admit or what not to admit as well as what to evict?
What do you mean, what to admit?
Like, does it admit everything to the DRAM, or is it possible to
Yeah, it kind of has to move it to the DRAM before you're going to access it. You can't go direct from disk very well, for example. There's a lot of intricacies in the design we won't get here, but just sort of, you have to shift your thinking if you've gotten used to the hardware caches and cache lab. You have to kind of shift your thinking that virtual memory has the same ideas, but because of where you are in the technology space, it's a way different engineering design. It's like the difference between designing a jet versus a car. You just kind of, they both move, they both have engines, but they're very different parts of a design space. And the other fact is that it's always a write back, that because the cost of evicting something, or the cost of a write is very high. One thing I should mention, I keep talking about magnetic disks, and as you know, increasingly, those are disappearing from even your laptops. Mostly have solid state drives, as well as my phone doesn't have a spinning disk in it. The old iPods, if you remember, these would be antiques for you, actually had little disk drives in them. They're pretty cute. But the really old iPods, the really old iPods. So now it's all based on what's called flash memory. And flash memory is not DRAM and it's not SRAM. It's a third type of memory that's based on a way of storing a charge in a sort of essentially a capacitor that can hold charge, and it's designed to hold it for a very long time. So flash memory is very different from disks in that it doesn't have mechanical spinning, and a lot of what I said isn't really true. But it is the case with flash memory that its access time is slower than DRAM, and especially its write times are much longer than its read times. So anyways, the transition from mechanical disks to flash memory has changed some of the parameters, but still the same general system support, hardware support, and software support is used for what they call solid state drives as compared to magnetic drives. So the idea of keeping track of this mapping between virtual pages and physical pages then is handled by what's called a page table. And a page table is just a set of entries for each of the pages that are potentially referenced by your program. So for every virtual page, we'll get into this in some nuances, but think of it initially as there's a page table entry somewhere that the operating system maintains and has access to. And what that will have is it will have various little 1-bit flags, the simplest just being the valid versus invalid. And then if it's a valid page, meaning it is represented in physical memory, then it will have the number of the physical page. So so think of it as just a table where each page table entry then has some information about that page, including is it resident in the physical memory, and if so, where? And for all the other ones, it will have some reference for where on the disk. We'll just assume disk still. Is the actual page stored. And for pages that are invalid, we'll just have a null pointer there. So at any given time then, what happens if we reference some word, we'll get a hit if that word is located. What that means is that the processor will, or the memory management unit will look up the what page of virtual memory does this represent, look at the corresponding page table, and if that page is located in memory, that's called a hit. And if it's not in memory, then it's called a page fault. And what that will do is trigger an exception, just like we've seen talking over the past week or so, the idea of exceptional events. It will trigger an exception, meaning it will interrupt the running program and invoke the operating system. And then what the operating system does is it will, assuming the physical memory is fully occupied, it will pick some page to be evicted, in this case, this final page here, VP4, and it will write that back to the disk, and then it will move the correct page in, and then it will return back to the original program and re-execute that same instruction as before. So we told you with ECF that you might sometimes have an exception where the return is back to a new instruction, but this is a case where it'll go back to the original instruction, which caused a fault before, but now that will go through because the page that's needed is located in memory. So this is sometimes called demand paging, just like what we talked about as demand caching, meaning that when we talked about caches, the idea is that the operating system doesn't try and predict in advance what the access pattern is going to be like. It just waits, and when it's asked to reference a page that it doesn't have, it will bring it in, and it will chug along, and then if there's so it only reacts and brings in pages in response to the particular demands being made. And in general, if we want to allocate new space for the memory, then we don't actually have to, like if you, for example, if you're calling, when you're first starting up a program, for example, and there's all these, the code and the data that's part of your address space. It doesn't actually, when that program first gets loaded, it doesn't actually bring that into the physical memory. It just, that code, the binary file, is actually sitting on disk, and it will just create pointers to those locations on disk where your code is stored and the initial values of any data. And then when the program first executes, what will happen is it'll create a whole series of page faults that then bring your program and the initial data into memory, and it starts executing. So this mechanism, once you have it, gets to be a very useful thing for handling a lot of the kind of low-level activities that a program has to do. And so the reason this works is, again, just like caches, it works because of locality, that you tend to access only relatively small regions of memory at any given time in your program. And so there's a term they use that was developed, referred to as the working set principle, meaning that there's sort of some subset of your total memory that you're kind of actively using at any given time. And as long as that's no larger than the physical memory of your computer, then virtual memory will work. If you have an application where it's making references all over the place to a huge range of addresses, then virtual memory will just fail totally. You'll often see this on older machines when there were these disk drives. You'd hear the disk going, or on really older machines, the disk was this thing like this, and that thing would just start to shake because it was trying to, the pages were basically, the memory system was thrashing. It was grabbing a page off a disk, bringing it in, making a few changes, need another page, evict that one, bring it in, and the program performance just totally takes a nosedive because you're going from access times measured in nanoseconds to access times measured in milliseconds. So that's sort of a reality that you can only, virtual memory only works as long as the sort of reality of the system can make use of the actual physical memory. So that's then the idea of caching. Let's go on and talk about memory management. And this is where I said that you have many processes running, each of which has its own virtual address space, but somehow they manage to get along. And this is this idea that once we have this idea of an indirect mapping between virtual addresses and physical, then we can have it where different processes have different mappings. And so, and you can even have sharing potentially, as this example shows, of VP2 in both of these cases represents a shared page in the memory. And this is one trick, for example, if you have a shared library like of code, instead of having 100 copies of that same code to support 100 processes, they can all be reading from that same part of the memory by sharing this page. So that's a good thing. And you remember with fork, that fork conceptually creates a clone of a process so that now from thereafter the two are running kind of side by side but with separate copies. Well, the mechanism, we'll go into that a little more, doesn't require actually making an exact copy of the full memory. What it does is it just creates a shared region. These two processes are basically sharing their pages. But it also makes sure that if one of them goes to and then does a write, at that point it will basically create the copy so that the two have independent updates, right? Because you remember they both got copies, but thereafter they were like isolated from each other. So the operating system does that by sort of this trick of saying, well, as long as you're not doing any writes, you don't have to know that you're sharing. And as soon as the write occurs, I'm going to just clone that copy, and now we'll have two copies. So it's a pretty clever trick. And for example, that's an easy way then to get sharing of the code libraries. So that's the idea then, as soon as you have this indirect mapping, it's a fairly straightforward idea to have this independent processes that have some shared pages but mostly unshared pages. And as I mentioned, it also simplifies how linking is done. Linking and loading. Linking, remember, is how all the pieces of code get assembled into executable file. And the good news is that executable file can just use its range of virtual addresses and not have to worry about are two different processes going to share the same memory region. And loading, as I mentioned, once you have this mechanism that can just bring in memory off the disk and make it become part of the memory that's used by a process, then that's sort of the underlying mechanism of how exec fires up a job, the loader. It just creates a pointer to the disk positions of the code, and then those all are brought into memory by page faults. Question?
So a page table only holds the addresses and maps, and then the virtual address space, that's what actually holds the real pages, right?
Yeah, we're going to talk in just a minute about, when I talk about address translation, we'll go into more what page tables are like and how they're stored and what their format is.
But they don't have the actual pages on them, right?
No, a page table you can think of as just an index for mapping for this virtual page, where is the physical page, okay? It's just a table. And the idea of pages, though, is that we've partitioned the memory space into these blocks of so many bytes. And so we don't have to have for every byte, where is it stored? We just have, for this range of bytes, where are they stored. Right. Good? So here's actually a little bit more about page tables. That we can add various little flags to the page table entry that give information about what privileges are allowed for this particular page. So in this case, we say, does it have access for the supervisor, in other words, the kernel? Is it able to do reads or writes, or can we execute the code here? Whoops, it's coming up. So imagine that just as part of the page table entry, we can store these little flags that indicate what's this range of addresses you're allowed to do. And we talked earlier, you remember with the attack lab, that back in the bad old days, on an Intel processor just stored a read and a write bit for each page. And there was no way to separately indicate whether that should be executable or not. And so since your stack had to be both readable and writable, it became executable. And that's what let people put on the stack code by code injection attacks and then have it execute like you did with your C targets. But nowadays, part of x86-64 actually, is there's yet another flag for each page that says, is this executable or not? And so the stack is marked unexecutable. So there's various flags that you could imagine having, but the point being that this whole mechanism gives you a way to control what types of access are permitted to which parts of the memory. I'll also mention, by the way we made your C targets so you could attack them was we actually allocated a separate chunk of memory and then sort of diverted the stack over to this other chunk. And that chunk was allocated in a way that let it be executable. Okay, so that's the idea, and we'll talk more about that, but let's go ahead with the quiz. You know, I think that was more conceptual. I don't think it's real. It meant supervisor, kernel mode. So does the operating system have access to it? But somebody made that slide up. That's not really on any real pages because the supervisor And a standard process has access to everything. But the kernel. Actually, no, that's not true. In Intel now they have a region of memory you can set up that's private. It's called an enclave, secure enclave, that even the kernel can't access. Okay, so I think we have, most people have made progress on this. Let's just go through the questions. I can make this thing work. So most people got the first problem correct. And this is, if there was a problem on a previous quiz that we didn't have time to get to, and this is a slightly changed version of that. So this one sort of tests some of these ideas about signals and the idea that proper signal handler, if there's multiple possible copies of signals coming through, it has to have a loop in it. The ways we've shown that before was always using sig_child, and this is just a variant on it. There's a couple of signals called sig_user signals that basically have no fixed definition from the operating system perspective, and you, the program writer, can use them for whatever you want. So this is the same idea, though, that instead of a sig_child handler, I had a handler for sig_user. And then this, whoops, little formatting problem. This main program would fork off 5 children each of which would send this signal to the parent, the main program, and then exit. And then then the main program would just wait until all 5 children had been completed. You see that this loop is every time a child is being reaped here, it will increment that counter. And then at the end, it asks how many times has this this handler been called. So, the correct answer, as you can see, is between 1 and 5. And you can see that pretty easily. It has been called at least once because that's the only way that this children counter gets incremented. But it could be as small as once, because it might be that the first time this handler gets called, all 5 children have terminated. All 5 children have terminated and can be reaped. And so the minimum number is 1, and that's the correct answer. So the main idea of this is to, again, remember that signals don't queue up. They're just a 1-bit flag for each signal type. And so you have to write a loop like this. The next one is a variant of these nasty file problems that always show up on exams. It's an amazing thing. And again, most people got the correct answer. And what you basically have to do on these is, with a pencil and paper, just work through what's going on. So the idea is that we open up 2 copies of the same file. And you remember those 2 will have independent position indicators as they read through. So typically, if you just open 2 copies and read in any order the 2, each of them would just see the copies, the values A, B, C, D, E, as they did successive reads. But because of this dupe 2, it means that first we read from the first file descriptor and got an A, but this dupe 2 then turned FD1 into a copy of FD2. And so now when we're reading from both FD1 and FD2, it's as if we're reading from the original FD2. So we'd get an A the first time and a B the second. And then finally, we've only very briefly talked about virtual memory, but most of this stuff is true. As we said, it's like serves as a cache where you use the DRAM as a cache for your virtual address space. It's a way to provide protection between processes and within processes so that they can't do anything harmful or restricts your ability to do harmful things. It allows sharing of code. But malloc, and you're gonna really know malloc really well in a few weeks, I can promise you that. But malloc is an interesting program because it doesn't require any synchronization. It's really just a function that runs within your own process and allocates and manages the heap memory for your particular program. But there's absolutely no synchronization between the various mallocs that might be executing at a given time, because each of them is managing memory within a separate or isolated address space. So I think most people got that, and so let's move on. Okay, so I promised to talk more about address translation, and the idea of, you already learned this idea of caching, the idea of looking at different bits within an address to figure out and interpreting to look up into tables and to create offsets. And it's the exact same idea with virtual memory, that there's a mapping between a given virtual address and its physical address counterpart, or potentially we'll say phi or null value if that address is not located in the physical memory. And then that will cause a page fault. So just in terms of some of the, we've already introduced these numbers, n, m, and p, n being the number of bits in a virtual address, m being the number of bits in a physical address, and p being the number of bits for which the page size is 2 to the p. So as I mentioned, 4096 is a very typical number. Might be bigger, might be smaller, but that would be 12. Little p would be 12 in that case. And so what we'll do is we'll break out the address, and I'll show you this in a minute, between the lower p bits, or 12 bits in our example, are called the offset within a page. And the upper, whatever is left up, is then called the virtual page number. Just like we saw with caching, that we looked for what's the offset within a block, and then what's the tag. Same ideas. And same way, we can talk about the physical pages having an offset, and then you're picking a particular offset is the position of this within the page, and the physical page number being the where it's located in physical memory. So in general then, the address translation goes like this, that we take a virtual address and we split off the lower p bits of it, and that's called the offset. And so that offset becomes exactly the same that we use in the physical address, right? Because we're assuming that we're going to load all these pages on multiple of the page size boundaries. And so now we can just use the same low order bits to index into the physical memory that we do for the virtual memory. And so really the translation that goes on is then the translating from a virtual page number to a physical page number. And that's what the page table entry has to hold, is it has to hold a copy of the identity of the physical page. And it has to, at the very least, have a 1-bit flag saying, is this a valid page or not? Somewhere there has to be something where it can keep track of where is the actual page table. And that will be a register that we really haven't talked about, but is, in other words, there's some hardware register that contains, identifies where in memory is the page table. Because one of the interesting things is the page tables sit in the same physical memory as the data, the rest of your program information. So somehow you have to know how to get to the page table. So the idea then is the overall scheme, if you work the whole thing out, is first of CPU, the program you're running wants to access, read or write some location in memory. So it gives a virtual address, and then the memory management unit will turn that into an address of a particular entry in the page table. So PTEA is the address of the particular page table entry that would hold this. And that's done exactly by, if you look at this, you can think of the virtual address conceptually is there's one page table entry for each virtual page number. So if a page table entry is, say, 8 bytes, then what you'll do is index, it's as if you index into an array using your virtual page name number as the index into this array to get to the page table number. So that's what we meant when I said a PTEA is just how do we locate this particular page table entry? It will be somewhere in physical, we're assuming it's going to be in physical memory. And then we'll read through the memory, and potentially it's stored in the cache, the actual page table entry. And then that page table entry will give us what the physical address of this memory location is, and then we'll give that back to the memory system, and that will give us our actual data that we wanted. So that's all the steps to a read. And you'll notice that in this scenario, it takes 2 full memory accesses, even in the best case here, where everything's a hit, to first find the page table entry, and then actually to locate within that page the data that we're trying to read. So that's kind of scary if you think about performance of a program. If every single memory access actually requires 2 memory accesses, that doesn't sound very promising. And it's even worse if there's a fault. And the fault can be, in our example, we're assuming the page table is in memory, but it might be the actual page you're looking for isn't. And so that will raise an exception, and then that will require the operating system to bring in that page somehow from memory and access it. So when you have a page fault, then it has to actually typically write a whole page out to disk, bring a new page in from disk, return to the original process, restart that faulting instruction, and then it goes through the same scenario for a hit. So overall then, this sounds like a fairly costly process. So obviously there's some tricks involved. And this slide just shows that typically the actual cache, the hardware cache, is the one that's really between the CPU and the memory system. And so a lot of these reads and writes will actually occur in the L1 cache, or one of the caches. But conceptually, just one thing to think about is caching from a program perspective is completely invisible. It just happens. It's all handled in hardware. Whereas virtual memory is this combination of some hardware support and a lot of operating system support. So this would not really work in real life if every memory access then required, in the best case, 2 memory accesses. So what the solution is to create yet another what's called a buffer, but it's actually a cache. It's essentially a cache of page table entries. And it's usually called a TLB, meaning a translation look-aside buffer. And so it's a translation buffered, but it's exactly, it is in fact a hardware cache of the page table entries. So it's a mapping from virtual page numbers to physical page numbers. So in other words, what it does is it contains the complete page table entries for some subset of the actual pages you have available. So now we can add to our mix then when we want to do look at the TLB, it's treated just like a cache, like the hardware cache that you've already seen. And so we can split the virtual page number into an index and a tag, and use the same ideas you had for set associative caches. So in other words, we'll say our virtual address then in this case will have this lower p bits will be the virtual page offset, but then the virtual page number, some subset of those will be an index that's used to index and select the proper set from a cache. And then your page table entry, if it's cached in this TLB, will reside somewhere in that set, just like we saw for the caching of data. And so what happens now with the TLB is that we avoid that extra memory reference. That what will happen is we'll issue a virtual address, that memory unit will use the virtual page number to index the TLB, and that will come back with the page table entry that we want. And then from that page table entry, we can generate a physical address and go off to the main memory for our memory reference. So you see that assuming a TLB is a hit, then we'll be able to avoid that sort of double cost of every memory access. And so that's pretty important. And it doesn't take a huge TLB to basically make this work really well. And so any kind of machine that supports virtual memory will have some kind of TLB in it. If there's a TLB miss, it will go through that double access process, but it will store the resulting page table entry in the TLB and get back to the processor. So that can all be done totally in hardware, as long as the actual page is resident. A TLB miss can be handled totally in hardware without slowing down the program very much. Okay, so that's sort of the basic idea. Now, life is less simple than that. Imagine, for example, we had an x86. I said it's a 4 kilobyte page, but it's 48 bits of address. And so if we work out how many how big would the page table be for that program, you'd realize it's an impossible number. 2 to the 39th is 512 gigabytes just to store the page table. Because you work out the numbers that basically out of this 48 bits, 12 of them will be the page table, the page offset, and so 36 of them will be for the virtual page number, and each page takes 8 bytes, so that's where this number comes in. So what happens then, and we'll show in the next lecture a more detailed look at the typical x86 processor. But the idea is to actually use a multi-level page table. And so the idea of this is that the level 2 page tables will actually be the standard page table entries. But the level 1 page tables will be basically a page table for pages. And these will actually be stored in the virtual address space, and only the level 1 page table will be in the physical address space. So in this 2-level scheme, we only have to have enough page table entries to hold this first level page table, and then these all can be stored in virtual memory and brought in by the same idea as paging. There was a question back there? Yes.
Why are you multiplying by 2 to the power of -12?
What's that?
Why are you multiplying by 2 to the power of -12?
Oh, in this calculation, that was taking away the page table size. So remember, the way one way to think about it is of the 48 bits, 36 of them will be the count of the number. 2 to the 36 will be the number of pages, right? And each page requires 8 bytes to represent. So 2 to the 48th times 2 to the -12th is 2 to the 36. Okay? But it takes a while to get your head around this. But imagine we're going to use imagine a case where you just had one sort of 4896 byte region of physical memory that holds the top level page table. And then that's all references other page tables, but they don't have to be in physical memory. They can be brought in and out by the same paging mechanism that we bring the regular pages. And so that gives you this ability then, with a relatively small amount of information, to keep track of all the range of pages in your program. Yes.
Oh, for your page table to be like 512 gigabytes, would that mean that your hard drive would have to be like really, really big?
Well, the other thing is, the question is, so, okay, what you're basically saying is, okay, great, so I get to store all these level 2 page tables on disk, right? But your observation is correct. With this number, we're still, we've blown a lot of disk space, right? And I've really blown it on my phone where I have, I think, 64 gigabytes of flash memory, right? So there's the main trick we're using is that real programs are never the full address space, or we really don't have, we really can't run a 256 terabyte program on my cell phone, right? It's just not going to work. So you really, a lot of these, even level 2 tables don't exist. If there's a huge region of memory that's unallocated, then you don't have to have page tables for that part of memory. Question? Yeah.
Why is the virtual address space so big then? Why not just, like if that's just not even possible, why not just make it smaller so you don't have to pretend that?
Yeah, you know, it's an interesting thing that there's this whole history of people making their processors assuming that, you know, nobody would ever want this much virtual memory, and so I'm going to restrict how big my addresses are. So the first computer I used for real was had a 12-bit, so 4096 words, they weren't bytes, of storage. And so there's this whole history of processors that only allowed 2 to the 16th, and then they became obsolete. And then recently 2 to the 32nd has sort of just gone over the edge where people routinely want more. And so I think what they said is, oh heck, we're not going to get caught in this again. We're going to really jump to something huge, anticipating that someday in the future, people might really want to have that size of programs. And as I said, actually in the Pittsburgh Supercomputer Center, they have this machine that has over a terabyte of DRAM on it. And it's shared between a whole bunch of processors, but in principle, any one of those processors can access any one of those positions. So there really are machines coming along today. They're very expensive, but there really are machines that exist today that where you're referencing terabytes worth of data. So we're not at 256 terabytes, but we're getting that direction. Also, you remember that even if you think about it, right now the hardware is limited to 48-bit addresses, but the actual pointer size is 64 bits. And so they're even anticipating some future in which you can have 2 to the 64 bytes of memory addressable. And that's a lot of memory. Yes?
What would the TLB look like in a scenario of multi-level page tables?
Good question. I think that the TLB stores entries can store entries at any level, and it has basically, you know, one of the parts of the entry is saying at what level of the page table is this particular one. That's a good question. So this is an example that this is just for simplicity, assuming 8 kilobyte pages and 8 bytes per page table entry. But this is the idea that we have basically these top level page table entries is now indexing into a range of, in this case, 1024 different page table entries, each of which is then giving some position for 8192 bytes worth of virtual memory. And so and as I said, that if there's some huge gap in the virtual memory system, then we don't need any level 2 page table entries to represent that. So it's sort of the classic use of a tree. So if you work out the numbers, 2 doesn't really do the trick, even for the 48-bit case. That it actually ends up being, I think, 3. We'll look at it more. But this same basic principle applies for any number of levels. That we basically were splitting the virtual address page number into k different fields, each of which then gives you an offset in some type of a page table that either indexes into a page table at the next lower level or next higher number here, or directly into the page table for the program data you're looking for. And in principle then, all of these, except usually the very topmost level page table, can be swapped in and out of memory, can be handled just like regular pages. And one thing you'll notice that's sort of very standard is that the page size is always the number of page table entries is always in other words, this particular field will be the size of 1 page's worth of page table entries. So just imagine 4096 is the case of x86, and each page table entry is 8 bytes. So there's 512 page table entries in a page, and so this will be 9 bits worth of address. We'll go into that next time, but that shows this idea of you view the virtual address as basically a big representation of a path through a tree, where the branching factor of the tree is determined by the page size. So as a programmer then, you're mostly hidden from the realities of virtual memory as an application programmer. That, in fact, virtual memory does this nice job of hiding a lot of nastiness from you. That you have a view that you have as much your own private address space that can't be corrupted by other processes. But then that puts a lot of weight onto the operating system and to some extent the hardware as well to manage all that virtual memory. But it does a lot for you. So I went back. Nowadays, only the sort of most primitive, smallest processors use physical memory. Back in like the early days of either the PC or the Apple Macintosh, and certainly Apple IIs, back in the ancient days, those didn't have virtual memory. And so it was very common you could have a program where one program basically caused the whole system to lock up because it had a wild pointer reference that screwed up the data for other programs. So it's really been a nice thing. You should appreciate that fact, that your programs are fairly isolated from each other through virtual memory. And so all these are features of why even for fairly, things like cell phones and most of the processors, even in an automobile, they really want to have virtual addressing just to kind of take care of all these features. Other questions? Yeah.
There's such a level of abstraction with virtual memory. What's the point of even trying to write cache-friendly code if like your attempt at trying to optimize cache is so hidden in all these levels of abstraction?
Yeah, actually, a really interesting question is why even bother trying to write cache-friendly code if there's all these layers of page tables and stuff? The whole scenario in all this paging and all these n levels of pages is almost the hit rates are measured in like 99.99%. So all the extra cost of doing it is almost invisible for reasonable programs. So if you actually, those caches, you can really see it when you write programs, that if you write cache-friendly code, it really runs 10 times faster than bad cache code. Now, for the transpose stuff you were doing was pretty much absurd, right? That you were, especially the 64 by 64 case where you're kind of picking up this and putting it there and this and there. So that sort of went over the top, but that basic idea in caches and what we call cache-friendly code is a real thing. Because especially for programs that really are pounding on memory and they're doing something like reading through arrays and things, all those pages are just sitting there and all the TLB entries are hitting. So all of this is working perfectly. And it really is then bound by the time to stride through the arrays. But that's a really important consideration, that all this only works because the frequency at which these bad events happen is so small that it doesn't significantly harm the performance of your program. But that's a very important design point. Yes?
So why do we need TLB if the table's probably going to end up sitting in L1 anyway, because we access it so much?
Well, L1 is still lots. The TLB basically gets you, we'll see that the TLB happens, actually there's this clever trick that makes it possible to do the TLB access and start reading the cache at the same time, because I can, usually if you look at the bits, the thing that selects the set you're accessing in the cache, all those bits are within the page offset. And so that part's the same whether it's physical or virtual. So it actually does the set access of the cache at the same time it's doing the TLB. And then only when the TLB then does its translation does that tell what the tag within the cache is. So the hardware can make it fast. And also L1 SRAM of L1 cache is still a little bit slower than, the TLB is a very small memory, and so it runs really fast.
Okay. And also, does every process get its own table to translate the addresses, virtual addresses?
Yeah, so the page tables are independent for every process.
Okay.
But TLB is shared. So when you do a context switch, you might have to flush out TLB entries for one process and put them in for them.
Okay.
And the caches usually caches are almost always referenced by physical memory. So it means I can run a program, jump over doing this program, and come back, and as long as those pages haven't moved and those cache entries are still valid, I can still get a good cache performance out of it. Okay? Good questions. Yes?
Does each process have its own set of registers?
Yes. So the idea of registers, let's answer this in two ways. The classic view of registers is that there's only one set, and if I do a context switch, what I have to do is copy that whole set of registers onto the stack, and then pull the saved registers for the other processor into the from the stack into the, in other words, memory, from memory into the registers, and then I can do it. That's the classic view. Now, most processors nowadays have what they call hyperthreading. And hyperthreading is actually where there's multiple copies of the registers so that the processor can jump between the two processes almost instantaneously. And it will actually do that. You saw in the code optimization that you have these pipeline functional units going on. It'll actually jump on an instruction by instruction basis between the hyper-threaded processes to let it fill up the pipeline with basically operations from different programs. But that's like we're off in outer space here. So if what I said didn't make sense to you, just flush it out of your memory. But that if you ever hear the term hyperthreading, that's what hyperthreading is. Other questions? These are good questions. Okay, very good. We'll see you next time.